Well, sorry we didn't get to meet today, but I am going to post these extra practice problems for Module 10. If you've not done the extra practice problems, they are on page 624 this time. And yeah, I hope my voice is easier to understand this video. I'm doing it a little bit differently. I may run out of space and have to do it in 2 separate videos, but that's okay. So let's start with number 1. If you are having trouble dissolving gas into a liquid, what should you do to increase the solubility of gas? We talked about this in class as well. For those of you who are divers, know that pressure and we talked about this when we did the soda experiment, not only pressure but also temperature affects solubility. We saw the most bubbles come out when we were boiling it, and the least bubbles come out when we put it in the ice bath. So if you want to dissolve a gas into liquid, meaning keep the bubbles in, you would want to cool it. You would also want to put it under pressure. That's why when you open a soda, all the pressure comes out. They keep it under pressure so that it stays fizzier. Okay, the following reaction is performed in a lab. And the nice thing is, this time, they gave you the equation. Okay. I hope I don't run out of space. Al2 carbonate solid plus, ooh, yuck, gonna have to go down here, KNO3 aqueous. Okay, so if you have 382 milliliters of 1.25 molarity aluminum nitrate, so we have 382 milliliters of 1.25 molar. So molarity is a solubility, is a dilution factor, basically. Molality is solubility. So this is dilution of liquids usually. The other one is dilution of solids. And we are trying to find, and we have excess potassium carbonate, how many grams of aluminum carbonate will we be to produce? So we're wanting to know this. Okay, where do we start? We know this, we're trying to find this. So let's find, so we know that 1.25 means mole over 1 liter. So we want to figure out how many moles are in this and then do some comparisons. So how many liters do we actually have? So 1 liter is to 1,000 milliliters, and we have 382 milliliters in this solution. So let's kind of figure out where that should give us moles. So we might want to actually list it like this: 382 milliliters over 1 times 1,000. Whoops, good thing I rewrote this because that's not right. For 1 liter times 1 liter, 125 moles. And that should give us the molarity of this specific compound. So let's erase this up here. Okay, handy dandy calculator. So 382 divided by 1,000 times 1.25. And we have 0.4775 moles. And this would be specifically AlNO3. I should have been technically writing that the whole time, but I didn't. So that is all one, it would be the same for all four of those. Okay, so now we know our molarity. Let's figure out, so we have milliliters, the molarity. We know how many moles roughly are going to be in this because this is in moles. We don't have to change from grams to moles, but we're going to have to change to grams over here. So here we have, let's see how many significant figures we have. So this is 3, so let's stick with 3. 1, 2, 3. So let's do 0.478 mole aluminum, is it nitrate, right? I think so, nitrate. And we'll put that over 1. So aluminum nitrate, and we're going to find, we have 2 aluminum nitrates on the left side in comparison, mole, whoops, that's in a mole there, to 1 mole aluminum carbonate. So when we do that, it will leave us with mole aluminum carbonate. So basically we just divide that number by 2 and I get 0.23875. You maybe got a different number because I actually just hit answer from my last time and then divided, so let's just double check. Yeah, by the time we round on the next one, 0.239 is what we will have, and that's moles of Al2CO3. Okay, so we're now in moles over here. We got to figure out the grams. Of course, 1 mole of aluminum carbonate is the same as how many grams of aluminum carbonate. We got to find our molar mass. So, CO3. So we know that 16.01 times 3, right there, plus 12.01 equals, and we're going to multiply that by 3 because there's 3 of those. That's our carbonate, polyatomic anion, and aluminum. We're going to add that twice just so I don't have to multiply. So we're going to 26.98 plus 26.98. So we're going to say 53.96 grams. I always do that a second time because I don't have you guys here to check it out. And we'll multiply that. There's our carbonate times 3 plus our aluminum, 26.98 plus 26.98. Well, that's a different number. See, that's why I do it twice. 234.08. Guess I'm going to be doing it a third time, huh? 16.01 times 3. That's our oxygen plus 12.01. Equal that. That's our carbonate. Multiply that by 3. Add our aluminum. Okay, so I'm going to stick with 234.08. Okay, now I'm going to multiply that by 2.39, and that should give us 55.94512, and that's grams of aluminum carbonate. But we want to make that nice and pretty for our sig fig, so we're going to say 55.9 grams of aluminum bicarbonate. Oops, there we go. That's what my answer I'm going to stick with. Let's see how I did that and what I did wrong, if I did anything wrong. Let's see there. I say 296. Oh, sometimes I have different numbers too. Let's see here. Yeah, they have 690.0 milliliters, and I don't have that. I have 382 milliliters. So that's where that went wrong. Yeah. Oh, I'm in the solution problems. Oops. How about getting to the right one? I went one too far. Ha ha ha. Oh, there we go. 55.9 grams. Looks, it helps if I don't go too far over. I went over a page too far when I turned the page. Like, that doesn't make any sense at all. Okay, so that's how we would do that one. Let's go to the next one. We'll probably do half, and then I'll do another half because they get kind of long. Okay, potassium cyanide can be made from the following way. KOH plus, and that's aqueous, which means it's suspended in water. HCN, aqueous, yields H2O, liquid, plus KCN, aqueous. Okay, so this is an acid-base reaction because we're going to be having an hydrogen move, which is the definition of an acid-base, right? So, how many milliliters of a 1.5 molar solution, HCN? So we're looking for how many milliliters of a 1.51 molar solution of HCN will be required to get 25 grams of potassium cyanide. Potassium cyanide right there. 25.0 grams. Okay, so we know that this is 1.51 mole over 1 liter. We know that. So why don't we start over here and go that way. 25.0 grams potassium cyanide. So much easier to write, so I'm going to. Over 1. Okay, we want to get this in moles, right? So 1 mole of potassium cyanide is equal to how many grams of potassium cyanide? We got to use our handy dandy periodic chart here. So we know potassium is 39.1. And cyanide is a carbon atom, which is 12.01, plus a nitrogen ion, which is 14.01. And that gives, whoops, I'll be doing that again. Potassium is 39.01 plus 14.01 plus 12.01. Okay, so we're going to say 65.12. And because you guys aren't here to check my work, I am going to do it one more time. 65.12. Good deal. Okay, so now we're going to have these 25 divided by that answer. All right, so this is 0.383906663 moles. We need to reduce down, okay, potassium cyanide. What was our sig figs? We have 3. 1, 2, 3, 1, 2, 3. That's 25, so we need to go 1, 2, 3. So we're going to say 0.383 0.84 mole of KCN over 1. So when we have these reactants, KCN, 1 mole of KCN, gotta compare it, we gotta get over here to hydrogen cyanide, is the same in this, the ratio from potassium cyanide to hydrogen cyanide is 1 mole to 1 mole. And I'm going to probably just keep going. Well, I would, but I'm not going to. So that all cancels out. So 0.384 mole. We're now in, hydrogen cyanide. We are now in hydrogen cyanide. So now we're going to put that over 1 mole hydrogen cyanide over 1. Okay, so now we're over 1 here. We got to get our molarity to be able to get to milliliters. So we know that 1.51 mole of this hydrogen cyanide per 1 liter hydrogen cyanide. And we want to multiply with 1 liter of hydrogen cyanide. It's the same as 1,000 milliliters of hydrogen cyanide. That should give us milliliters. Okay, so let's divide that by 1.51, and multiply it by 1,000. And I got 254.24 milliliters of hydrogen cyanide. Now we got to think about sig figs, which is 254 milliliters of hydrogen cyanide. Okay, let's see what the book says. Okay, just 1 page. Yep, that's what it says. Good deal. Okay, what's the next one? Copper is mixed with nitric acid for the following reaction. We have 3 copper solid plus 8 hydrogen, what did they say that? Nitric acid. It's like an aqueous solution. Yields 3 copper nitrite. And NO, 2NO to be exact, it's a gas, plus 4 waters. Okay, so we're looking for HNO3, where is it? HNO3, I put that, whoops, HNO3, so we're looking at this. We have a 3.50 molar solution. How many milliliters do we need? If we have 500 grams of solid copper. Look at that. I couldn't imagine the expense of that. Okay, so I want to make sure of HNO3. Okay, they want to completely use up 500.0 grams of solid copper in this reaction. So they want to completely use it. So usually you have products and reactants and products, that we're dealing with. But you can do stoichiometry this way too, honestly. Okay, so what should we start with? I would probably start with our 500.0 grams copper over 1. 1 mole of copper is how many grams of copper? Let's see here. There it is, 63.55. Okay, so then So we are going from grams. Whoa, what am I doing? One day. Okay, I will get this. So we said that was 63.55 grams copper for 1 mole of copper. So let's get that going. So 500 divided by 63.55 equals 7.86782 moles of copper. Okay, so we want to stay true to our sig figs, which 3 is our smallest. So 7.87 mole copper. 7.87 mole copper over 1. And we know that there's 3 moles for every H of, and I need to put mole here, copper for every mole of hydrogen nitride. Okay, or what did I say? That was an acid, nitric acid. So now we should be able to have moles of nitric acid. All we have to do is take that answer. I'm going to do both. I'll take that answer, divide by 3, and multiply by 8. And we should get 20, oops, I don't need a line there, 20.9808. But in case you clear it out, 0.87 divided by 3 times 8 equals 20.986. So if we're doing sig figs, it's going to be 21.0 mole nitric acid over 1. Okay, so now we're in moles. We're over here. Now we know that molarity is 3.5 moles of nitric acid over 1 liter of nitric acid. And we know 1 liter nitric acid is the same as 1,000 milliliters of nitric acid, which should put us into milliliters of nitric acid. Okay, so, whoa, we don't need logs of anything. 21.01, oops, we don't need the 1. 21.0 divided by 3.5 times 1,000 equals 6,000 milliliters. Seems rather large, but that's right. So let's see what the book says. Or 6 liters. Yep. They want to know how many milliliters. So technically, all those off to the right are not significant figures because you can move them. But they have it as 6.0 times 10 to the 3rd. But you can also say 6 liters too, which is what they have.